last lecture we discussed the operation of a switch mode rectifier and a bidirectional power converter. In both these converters, the magnitude of output voltage should be higher than the peak of the input voltage. And second point is, in the case of SMR, with the fixed hysteresis current control, switching frequency is a function of load. Switching frequency varies with the load, whereas this switching frequency remains constant in the duty cycle control. But then in the current control, inductor current is always continuous. There is always a current flowing through the inductor. Current is controlled within a hysteresis band, whereas inductor current is discontinuous in the case of fixed duty cycle control. Okay. I told you that the magnitude of the reference current or the duty cycle is determined by comparing the actual output voltage with the desired. Okay. Basically, what are we doing? We are storing the energy in the inductor and transferring it to the output. So, if there is a power balance, in other words, if the input power is equal to the output power, capacitor voltage will remain constant. Now, assume that you had connected some load. Remember, load is always an independent variable. You can go on change the load, and there is no information about the change in load at the output. In other words, the system is operating in open loop and you have not changed the magnitude of the current or the duty cycle. There is going to be a mismatch in the input output. Now, if it happens that load has decreased and source input power has remained constant, capacitor voltage goes on building up. So, all the equipments, all the components have their own voltage ratings. So, if the voltage increases above the rated, capacitor may get punctured. The same output voltage appears across the switch as well as the diode, the blocking diode. So, they may get damaged. Therefore, all this boost converters, SMR or bidirectional power converters, closed loop control is a must. Remember, closed loop control is a must in SMR as well as the boost converters. Any boost converters, closed loop control is a must, because input condition, input quantities are derived by measuring the output. Okay. So, open loop control is not possible. The other point that we discussed was, in a single phase SMR, even if the source current is sinusoidal, the input power has a pulsating component. Input power pulsates at twice the supply frequency. Therefore, if the input power pulsates, capacitor voltage also will pulsate. Therefore, it will have a second harmonic ripple. Okay. So, relatively the size of the capacitor is bigger to reduce this ripple. Okay. So, second order ripple is invariantly present in a single phase SMR or a bidirectional power converter. What will happen in a three phase? We know that if the three phase system, if the current is sinusoidal and the voltage is also sinusoidal, instantaneous power is always constant. I hope you remember, instantaneous power in a three phase system, when both voltage and current are sinusoidal, power is constant. So, if the input power is constant, So capacitor voltage will remain constant. So there is no lower order harmonic, in other words 6f, minimum ripple in a 3 phase is 6f, is not there because power is constant. So I need to have a very small filter in the case of 3 phase to eliminate high frequency ripple. Okay. So there is no 6 times the supply ripple in the output in the case of a 3 phase SMR with sinusoidal current or 3 phase bidirectional power converter with sinusoidal currents. Okay. Remember. So we were discussing bidirectional power converter. So though the source voltage is sinusoidal, input voltage to the bridge, this is the voltage at the input terminals, is non-sinusoidal, okay, is a stepped wave. Okay. So this stepped wave has its own fundamental component. So in other words, there is a voltage source here, an inductor, another voltage source. So two AC voltage sources are connected through an inductor. Okay. Therefore power transfer can be controlled by controlling delta, where delta is the angle between these two voltage sources. Okay. So one way to control power is by controlling the angle between these two voltages, or by varying the in phase component of the source current. After all, power transferred is V1 VAB x divided by x into sin delta, or Vi into I into cos theta, where cos theta is the angle between V and I. So by changing the in phase component of the source current, you can control the power transfer to the bridge. Okay. So control philosophy here is, sense the capacitor voltage, that has to be controlled, and if it remains constant, there is a balance of input and output power. Okay. So if it changes, either change delta or the magnitude of in phase component. Okay. That is the philosophy. But then if these two voltage sources are in phase and magnitudes are not the same, power transfer is 0. Okay. In other words, this can happen only when if I neglect the total losses. This can happen, remember, if both the voltage sources are in phase and magnitudes are not the same. In that case, power transfer from the source to the inverter system is 0. This can happen only when inverter is lossless and at the output capacitor is not supplying any load. In other words, the output terminals of the bridge, there is only a capacitor, there is no resistor. All this time I connected a resistor there, and I also told you that this resistor is not a must. This may be an input stage for other power electronic equipments. So if both the voltages are in phase and if the magnitudes are not the same, power transfer is 0 and the system can work only if the inverter is lossless, which I can maybe a fairly good assumption for the simple reason that losses in an inverter are very small, efficiency is fairly high, and at the output there is only a capacitor, there are no lossy elements. Now since voltage at two voltages at the two terminals of the inductor are not the same, current has to flow, and we found that if the magnitude of the voltage at the input terminals of the bridge, in other words VAB1 is higher than Vi, angle between the input voltage, input source voltage Vi and the source current is 90 degrees leading, okay, 90 degrees leading. So, this is equivalent to a source and a capacitor connecting a capacitor. So, entire the system, the inverter along with the inductor looks as if there is a capacitor, okay. And if Vi is greater than the voltage at the input terminals of the bridge, that is VAB1, this is a fundamental component, then we found that angle between Vi and the source current is 90 degrees, current lags the voltage. So, this is equivalent to a source and a pure line inductor, okay. The entire system, we connected a series inductor, 4 switches, capacitor, only capacitor, looks as if there is a L here, okay. So, just by controlling the magnitude of the voltage at the input terminals of the bridge, as of now I am calling these are the input terminals of the bridge, the VAB, I can make the entire system to appear like either like a capacitor or like a inductor. By the way, I have not told you how to control the magnitude of this VAB1. I am not going to tell you right now. Sometime later in the course I will come back and I will tell you, because right now if I try to explain you may get confused. Later in the course I will tell you how to control the voltage magnitude of VAB1, okay. Take it from me, it is possible, because the essential condition here is magnitude of capacitor voltages should be much higher than the input source voltage. If that is the case, I can have a higher or a lower component at the input terminals of the bridge. It is possible. I am not going to tell you right now, sometime later in the course I will tell you. Where will I use this system? A bridge, an inductor, and at the output side just a capacitor. Where will I use? Because if both the voltages are in phase under ideal condition, it is either a capacitor or an inductor. In non-ideal condition, what will happen? Losses are very small. So, what do I need to do? Instead of these two voltages are having in phase, I need to have a very small angle delta or a small in phase component of the source current. I will repeat, under non-ideal condition, inverter switching losses are finite, then I have a non-ideal inductor also. I have a non-ideal inductor, this is a non-ideal inductor, losses are finite, but then they are very small. So, what do I need to do? The angle between input voltage and the voltage at these two terminals, delta, should be very small, may approach 0, or I need to have a small in phase component of the source current. Vi into Is cos phi should be equal to the power that is dissipated in the internal resistance of the inductor and the losses. Under that condition, yes, of course, you should not have this resistor. Okay. Now, where will I use this system? This entire system, where will I use? Now, I will just divert and take back to power transmission. We know that most of the loads are inductive in nature. So, therefore, we need to have, if you are a bulk consumer, your power factor cannot fall a certain value. If it falls below a certain value, power tariff is going to change. Plus, if the power factor deteriorates, there is going to be a voltage drop at the load terminals, because generation is usually at a constant voltage. So, for a given power, if the power factor deteriorates, the magnitude of the source current increases. P is same, power factor angle increases, so cos phi decreases, so therefore I has to increase. So there is going to be a line drop, voltage at the load terminals decreases. All these factors you have studied in a circuits course. So what do? General practice is to have a capacitor at the load terminals to improve the power factor. Do you connect a capacitor at the load terminals to improve the power factor, or in other words, maybe voltage support or supplying the reactive power to the load. And I do not know whether you have encountered this situation or not. When the transmission line is lightly loaded, voltage at the far end of the transmission line may be higher than the input voltage, the so called Ferranti effect. Now at that time I need to connect an inductor in parallel, okay, just to bring down these voltages, okay. So in power factor improvement, there may be cases where you have to connect a capacitor across the load, or in a transmission line you may have to connect an inductor, okay, when the system is lightly loaded, in order to bring down the over voltages. So can I have, or can I implement these two schemes using the bridge that I showed you just now? And I told you that this bridge can either work as a capacitor or it can work as an inductor, okay. In principle you can use this, okay, you can use this. I will just give you an example as to how to use this as a capacitor, or how to use this to improve the power factor. See, consider a case, source supplying a load here, okay. If it is a passive RL load, fine, current is just lagging. Now if I have a nonlinear load, assume that this load is nothing but a SCR bridge feeding some other load, a DC motor or whatever. In other words, some nonlinear load, okay. The moment this is a nonlinear load, this current is lagging. We told you that if there is a SCR bridge, power factor is a function of alpha, and if I had assumed the source current to be constant and ripple free, sorry, load current is constant and ripple free, then source current is going to be a square wave. In a single phase case, predominant harmonic is 3rd, 5th, 7th, and in a 3 phase case it is 6 and plus or minus 1, 5th, 7th, 11th, 13th, okay. And I also told you that there are various standards wherein you cannot pollute the voltage at the point of common coupling, point of PCC, okay, because if you start drawing a non-sinusoidal current because of the line inductance, voltage at the load terminals or voltage where the other loads are connected is going to be non-sinusoidal. Recall, I have explained all this. So now load is a non-linear, that is determined by the nature of your system. So it will draw a harmonic current that should not flow into the system and pollute your voltage at the point of common coupling. So what will I do? Now I will connect a bridge, a capacitor, an inductor, okay, whatever the system that I discussed just now, okay, across the load, okay. Now if I make voltage at these terminals higher than this can supply, this system appears as if like a entire system, this entire system appears like a capacitor. Okay. If voltage at these terminals is less than voltage at these terminals, okay, this entire system appears like a capacitor. Okay. In other words, I am connecting a capacitor across the load. Okay. So by connecting a capacitor, we know that by connecting a capacitor it can supply, it can compensate the load. So I will control now the source current IP, which is sinusoidal and in phase with the input voltage. Alright? Okay? I said load is non-sinusoidal, load current is non-sinusoidal, okay, and it is lagging. I am connecting this unit which appears like a capacitor. Now the capacitor can supply the lagging component of current to the load. So if I choose this value of the quadrature component of current, the source will supply just the active component. But I also told you that in addition to the quadrature component of current, there are harmonics present in the load current. These harmonics source should not supply, or these harmonics should not flow back to the source. So I should have some sort of a harmonic generator which generate harmonics in the opposite sense. Okay. If the source, if the load has a third harmonic current of magnitude x, I need to have a harmonic generator which should generate the third harmonic whose magnitude is minus x. So this unit should not only supply the quadrature component of current, it also should supply whatever the harmonics that are present in the load current. Okay. So this load is a nonlinear load, has a lagging component as well as harmonic current. Source should supply only the active component of current. This bridge should supply the harmonics as well as the quadrature component of current. Is it possible? In principle, yes, it is possible. There are systems like this. Okay, I will just explain you very briefly the principle of operation. In SMR, in a current control, what did we do? We controlled the source current in such a way that it is in phase with the source voltage and it is sinusoidal. I will repeat, in SMR with current control, we controlled the source current within a hysteresis band, therefore it looks like a sinusoid and it is in phase with the input voltage. In other words, in this scheme, source supplies only the active power. Now you may say that it is not a pure sinusoid, agreed. But then if the hysteresis band is very small, the frequency of the harmonic that is present is also very high and they can be easily filtered out, a very small filter, that is not a problem, or they may eventually get filtered out by the line inductance itself. Okay. So if I make or if I control the source current, even in this case, which is sinusoidal and in phase with the input voltage, source sees as if it is feeding a purely a resistive load. whether the load is lagging or whether there are harmonics in the load current, it does not matter to the source. Okay, I will repeat. If you make the source current a sinusoid and in phase with the input voltage Vi, then source is as if the entire system load with whatever the compensator that I was talking, as if it is feeding to a resistive load. It is feeding just a resistive load, but actual load is maybe a lagging load, or it can have lagging as well as the harmonic load, does not matter. Who supplies this harmonics? Who supplies this harmonics? At any given point, KVL has to hold good. At any given point, KVL and KCL they have to hold good. Okay. Kirchhoff's current law and voltage law, they have to hold good. Okay. Whether you are doing power electronics or whether you are doing some other electronics, does not matter. Okay. So if I apply KCL at this node, IP plus J into whatever current, I will not call it as quadrature component now. Okay. I will not call it as a quadrature component. Some IC, IP plus IC should be equal to IL. Okay. So if I told you that source current and voltage are in phase, this IL has the reactive component as well as the harmonics. So the reactive component and all the other harmonics should come from the compensator. Okay. So if the load is non-linear, and if I use this system, okay, and control the source current in such a way that the current supplied by the source is in phase with the input voltage, all the remaining things including the reactive power is being supplied by the compensator. Okay. Remember. Now how do I control this IP? By switching these devices. Okay, very simple. Control IP by switching these devices such a way that this current is in phase with the input voltage. So whether source has harmonics or reactive power, does not matter, everything is being compensated by this. So hence the name VAR compensator, it supplies VARs to the load as well as it is filtering, or as well as it is supplying all the harmonics that are present in the load. In other words, it is an active filter, not a passive filter. Why active? As the load current changes, harmonics also may change. Okay, harmonics also may change, or harmonics will change, but the source current is just supplying the active component of current. So as the load changes, as this output condition change, compensator has to change the current that is being supplied by it. Okay, please, I am not calling this as a JIQ. Now it will supply JIQ only if a quadrature component of current, only if the load is passive and linear. Okay, no harmonics. If it has harmonics, the load has harmonics, compensator should supply the quadrature component of current as well as the harmonic current. Okay. So this unit is known as VAR compensator and active power filter. There are a lot of literature is available, okay, in the papers. I encourage you to read, okay, in the library. Okay. I will stop here. I will go to another topic. In the previous case, for the same bridge, what did you do in the positive of? We closed S4 only. We closed S4 only. So, current flowing from A S4 D2 back to source, and in the negative of we closed only S2. So, current is flowing S2 D4 back to source. So, we wrote the Kirchhoff's voltage equation. So, when I close the switch, di by dt is Vi divided by L, and Vi is the instantaneous value of the input voltage. But then instantaneous value of the input voltage itself is changing, and near the zero crossing Vi is very small, okay, near the zero crossing, positive or negative both. So, low L of theta sine function is 0. So, the forcing function itself is 0. Since the forcing function itself is 0, there is an inductor connected in series, rate of rise of current is going to be very small. So, in other words, it may not be possible to control the current within a hysteresis band, or in the fixed duty cycle there will be a very small current. Most of the time you have a discontinuous period. Remember, we fix the duty cycle in such a way that current is just continuous near pi by 2. So, most of the cases, most of the period, the remaining period current is discontinuous, and the period for which the source current is 0 increases as you go towards 0 or 180. At pi by 2 it is just continuous, at pi by 2 it is just continuous. So, as you go towards other direction 0 or 180, 0 voltage, 0 current period goes on increasing. Okay. So, near the 0 crossing in the fixed duty cycle most of the time it is 0, it is discontinuous period, and if it is a hysteresis control you may not be able to force the current, or most of the time you have to close the switch. So, you may have hysteresis control something like this, it may not be able to control, force the current. But then the bridge has 4 switches. Bridge has 4 switches. I haven't told you anything about the upper S1 and S3, because when I closed either S4 or S2, and I just opened S4, S2, current was flowing through the diodes. Now the question is, can I close these switches, or can I use these switches and try to overcome this problem? Okay, the problem of making a current sinusoidal even during the near the 0 crossing. Yes, it is possible. Now, instead of closing S4 only in the positive of, you close S4 as well as S3 in the positive of. Okay, you close both S4 and S3. How does the equivalent circuit look like? See here, I close both S4, S3, currents flowing positive of flowing in this direction, okay, thus through the capacitor, negative, positive, comes like this, this flows in this fashion in S3, okay, back to source. Okay, see, I will just show you S3 is in this direction. So, if I close S3, current will flow this way, current will flow this way. Okay. So, what is the KVL says? It is di by dt now, L di by dt is Vi, this is plus, this is aiding, these two voltage sources are aiding now, Vi plus V naught divided by L, Vi plus V naught divided by L. So, even if Vi is very low, V naught I told you generally is held constant. So, rate of rise is higher now. Okay. So, even near the 0 crossing I can have a fairly high di by dt. Okay. Now, you may say that, sir, Vi will attain a peak value, at that time what will happen? Yes, rate of change is much faster, much faster. So switching frequency will increase. So that's what, whatever you do in life you have to pay a price, nothing comes for free. So if you want to improve the source current waveform, so use two switches, use the capacitor voltage to aid the source current di by dt, current waveform becomes superior, but then switching frequency increases, because now di by dt, positive di by dt is Vi plus V naught divided by L. V naught is held constant and magnitude of V naught is much higher than the peak of Vi. So if Vi is low, things are not all that bad, but Vi will attain its peak value. So di by dt is higher than 2 Vm by L, because V naught is much higher than Vm. So di by dt is much faster as Vm increases. So we do have a problem, switching frequency will increase, but then current waveform is superior, can have a fairly good current waveform. Yeah, by closing S4 and S3 in the positive half, switching frequency increases, current waveform improves. What happens to the voltage at the input terminals of the bridge, that is VAB? Will it remain the same? Waveform will remain the same, or it's different? It has to be different. Let's see. When I closed only S4, VAB was 0, because current started flowing S4 D2 back to source. So voltage at these 2 points is 0, isn't it? When S4 is closed, there is a short here, diode is conducting, so VAB is 0. Okay. Now when I am closing S4 and S3, point A is connected to the negative polarity of the capacitor voltage, okay, at this point. B is thus, if it is connected here, so VAB is minus V naught, in the first case it is 0, and in this case it is minus V naught, okay. And when I open the switch, what happens? Current starts flowing the same through D1 and D2, the positive, and VAB is V naught, So voltage waveform now varies from V naught to minus V naught. See the transition, and it's quite fast, minus V naught to V naught at these terminals, okay. This is the change in the voltage waveform. Now all this time we studied about source supply power, only active power. If the current angle between the source current and the voltage is 0, source sees a purely resistive load. If in a bidirectional power converter, if the source voltage and the out voltage at the input terminals of the bridge, that is VAB, they are in phase under ideal condition and the magnitudes are different, source is either an ideal capacitor or an ideal inductor. I called in the beginning it is a bidirectional power transfer. Can I transfer the power back to the source at unity power factor? Okay, there are 4 switches. I told you that now current can reverse. I have bidirectional switches, but I have connected, since I connected a capacitor at the output, voltage cannot reverse, okay. So in other words, if I connect a battery here, please now you have to remove this resistor. I need to have an active load, only active load will supply the power back to the source. Okay. So, if I have a battery here, battery can supply power back to the source, current can flow through these switches back to the source. Okay. Please, no R here, resistor cannot supply the power, it can just dissipate it. Okay. So, or any other system, if I have a capacitor and continuously power is being coming from this side, power is coming from this side, yeah, it can flow back to the source. Okay. And that too at unity power factor. How should I do it? So, in this, at unity power factor it receives, it supplies, angle between them is 0, if it receives at unity power factor, if angle between them is 180. Okay. I take the current which is out of phase with the input voltage, control the switches such that this current is within the hysteresis band. Of course, there are other control techniques also. It's not, you can make the source current out of phase by 180 degrees, you can using other techniques also. Simple control technique is using current control. Okay. Is out of phase with the voltage by 180 degrees, control it within hysteresis band by turning on and off these switches. Okay. Simple. So, it is like this, close S1 S2, what will happen? C, or in this case I have connected a C assuming that capacitor is being continuously charged by other source that is connected at these two terminals. Okay. Or I need to have a battery here. Okay. So, assuming that power is coming from these two terminals, it can flow back to the source this way. Okay. Same philosophy, if I keep the voltage, if the capacitor voltage remains constant, there has to be a power balance, and voltage and current are out of phase by 180 degrees, source receives power at unity power factor. So, that power has to come from other source which is connected to these two terminals. Okay. Or if I have a battery supplying power. Okay. And this voltage is higher than this, the conditions remain the same. Openness, what will happen? Current, this direction of current should remain the same. So, it starts flowing through D4. So, this is the path. This is the path. So, this converter can acts like a bidirectional power converter. Source can receive even at source power at unity power factor. So, almost all the possible functions are possible. Yeah, we are almost through. In other words, we have completed AC to DC conversion, a major part in power electronics course. Okay, I have those, you can have more than one course in AC to DC conversion. I tried to cover in around 12 to 13 lectures, just to try to give just an overview. Okay, I started with half wave rectification, then we did half controlled, we did fully controlled bridge, both single and three phase. We found that power factor and harmonic spectrum, they both are poor. In half wave there is a DC component also. If the bridge is excited by a single phase supply, there is only one pulse per half a cycle. The ripple in the output voltage, there are only two pulses per 360 degrees or 1 pulse in half a cycle in a single phase case. So, ripple frequency is twice the supply frequency. There are 6 pulses in 3 phase bridge. So, ripple frequency is 6 times the supply frequency. Okay. So, something like this, I hope you remember. For alpha is equal to 0, 3 phase uncontrolled bridge. So, this is for alpha is equal to 0 for a single phase bridge. So, if I want to have a constant DC, I need to have a very small capacitor here, because this voltage is approximately constant. This is root 3 times, this is 1.5 times, okay, approximately constant, 1.5 to 1.713, whereas this is varies from 0 to Vm, and I want a constant value. So, definitely filtering in this case is minimum, out here is much more than this. Okay. So, what did we study after that? When I said as the number of pulses in the output voltage waveform or as the number of pulses in the source current increases, harmonic spectrum improves, power factor also becomes unity, power factor also improves. So, that is nothing but a PWM converter. How do we control the output voltage in PWM converter? By changing the modulation index. In a sinusoidal PWM technique, there are large number of other PWM techniques, okay. And in PWM converter, what happens is magnitude of output voltage is less than or equal to or is less than the input voltage. Then we studied switched mode rectifier. They are also known as the boost converters. We control the SMR with fixed duty cycle and controlling the inductor current, that is same as the source current also, rectified. Source current is the inductor current. There power factor is unity, okay. But then output voltage of switch mode rectifier or the boost converter is should be higher than the peak of the input voltage. It is almost an essential condition. Another essential condition is these converters should be working only under closed loop condition. Closed loop is a must. Closed loop is a must in switch mode rectifier as well as the bidirectional power bridges, or if I use this bridge to improve the power factor, or if I use this bridge as a war compensator or active filter, closed loop control is a must, okay. Closed loop control is a must. Bidirectional power transfer at unity power factor is possible. Plus or minus war, leading or lagging war supply is also possible. Online correction of harmonics is also possible, okay, using a single phase or a 3 phase bridge with self commutating devices, 6 self commutating devices, all these things are possible. So, we are almost through or completed AC to DC conversion. There are a lot of things are still left. If you have followed whatever that I covered, you can open any textbook or you can open any papers and try to understand them, okay. I just try to give you the principle of operation that remains same for other power topologies also. There are large number of topologies in SMR. I just did replace the inductor. You can replace the switches also. I used only one switch in the DC link, on the DC side. You can put that device or replace that switch, or you can transfer it to the AC side, have an inductor and AC side. There are large number of topologies, okay. So, principle of operation is the same, close the switch, store the energy, open the switch, transfer it to the output. This is the principle, there is no much difference. There are various control schemes also to control the active filter or to control the war compensator, war supplier. Okay. Now we will do another topic, an important topic in power electronics, DC to DC converter, DC to DC converter. Okay. This DC to DC converters, where are they used? These are also known as switched mode power supplies, SMPS, switch mode power supplies. Generally, this terminology used for low power application. Okay. The same concept is used in high power, they are known as choppers. Okay. They are known as choppers. Chopper fed DC machine, an important application. Where it is being used? I have an input DC and I want an output DC. Why output DC? Variable output DC to control the speed of a DC machine. To reduce the speed from base to 0 or to increase the speed from 0 to base, I need to increase the voltage applied to the armature. I have a fixed DC. Don't ask me how did you get this fixed DC. There are various ways. In the sense, one of them may be whatever that we studied in AC to DC conversion, or I have a fixed bank of batteries. Okay, so batteries voltage remains constant. Now I want to have a variable output voltage. Or take for example, in metro, Calcutta metro, we have a 750 volt DC. Bombay to Igatpuri is 1500 volt DC overhead traction. Now if I want to vary the voltage applied to the armature of a DC motor which is used, I want to control it. Okay. So these are come under high power applications. So they are generally known as chopper fed. We don't say SMPS fed DC motor, please. The principle may be the same. In both the SMPSs, input is DC, output is also a variable DC. So if the power is high, if a DC to DC converter is feeding a motor, we will call it as a chopper fed motor, not an SMPS fed motor. Okay. And take any electronic equipment, say a power supply in a computer, or any sophisticated electronic equipment, TV, it requires a DC power supply. Yes, where am I getting the DC from? Yes, input is AC. I want a control power supply, regulated power supply for various ICs. Power level is not very high, few hundreds of watts. Okay. So I might have converted the input AC to DC and this DC to another DC, another voltage level. They are known as switched mode power supplies. Okay. So if I use a DC to DC converter in computers, on any electronic equipment, or for low power supplies, I will call it as SMPS. Or if I use the scheme or DC to from fixed DC, and I am trying to get a variable DC, I will call it as in high power application, I call it as choppers. Okay. More about it we will study in our next class. Thank you.